All right, welcome to Chapter 6, Section 1. We're going to talk about exponential growth and decay functions. What you will learn, you'll learn how to graph exponential growth and decay functions, and you'll also be able to use these exponential models to solve some real-life problems that you may encounter sometime in your life. Okay, and these are the two graphs that we're going to talk about. Exponential decay is the black one. It goes down from left to right, and exponential growth from left to right goes up. And we always go from left to right because that's the way we read. So the red one is going up, so that's a growth, and the black one is going down, so it's called a decay. All right, let's get right into it. Here is the equation for a general exponential function. Okay, y equals a b to the x. All right, and there's a couple rules that we need to know. When we're talking about these, a cannot be equal to 0. Okay, a cannot equal 0. And b is a positive real number not equal to 1. Okay, so b is a positive real number not equal to 1. So let's just write an example. So a cannot be 0, b cannot be equal to 1. So let's say 4 times 3 raised to the x. Okay, so a is not equal to 0, the b is not equal to 1, and it's got to be a positive real number, and we use x as our exponent. And that's why it's called an exponential function, because the variable is in the exponent of the problem. All right, so there's two types of these exponential functions we're going to talk about. The first one we're going to talk about is called an exponential growth. All right, so that's the one where from left to right it's getting bigger. All right, exponential growths have certain rules just like the general one does. Okay, so in order for this to happen, a has to be equal to 0, a is greater than 0, and b is greater than 0 as well. Okay. Oops, I'm going to go back. That is incorrect. I meant to say b is greater than 1. Okay. Also, b, so this part right here, whatever's inside the parentheses, is called your growth factor. There's a vocabulary there. We'll talk more about that when we get to it. But the rules for exponential growth, a is greater than 0, b is greater than 1. So let's write an example of a problem. So a has to be greater than 0, so any number bigger than 0. So let's say 6. B has to be greater than 1, so I don't know, let's say 3.5, and then we're going to raise that to the x. So when you have an equation that meets these rules, a is greater than 0, b is greater than 1, it's going to be an exponential growth. So the graph will look something similar to, from left to right, it's going to go up. Okay, and we'll talk more about these graphs in more detail when we get to them. But basically all you need to know, exponential growth, decay. A is greater than 0, b is greater than 1, must be a growth. Okay. Next one is exponential decay. All right. Still, a is always has to be bigger than 0. Okay. And this time, b is a little different. B has to be between 1 and 0. So b is less than 1, but b is also greater than 0. So I'm reading from the b out. B is less than 1, and b is greater than 0. So what are numbers that are less than 1, but yet bigger than 0? So b, essentially this is saying that b must be some sort of a fraction less than 1. A fraction that's less than 1. Okay, so for instance, y equals, so a must be bigger than 0, so anything bigger than 0, so let's say 4. And inside the parentheses, the b must be a fraction less than 1, so let's say 3/4. Okay, so 4 times 3/4 raised to the x power. And if that's the case, if your base of your power is a fraction less than 1, your graph is going to be a decay. So from left to right, it's going to go down. And there we have a exponential decay graph. Okay, so there's a lot of stuff in this first section. So let's just move right along. All right, so these are pretty easy. This just want to know, are the following functions a growth or a decay? Okay. So on this one, notice that there's not a number in front of this 4. So we're just assuming that number in front of the 4 is a 1. So our a is 1. Our b is 4. Okay, is that a fraction less than 1? No. It's a number bigger than 1, so this must be a growth. Okay. How about this one? The number, remember, if there's no number there for the a, we're assuming it's a 1. Our b is 2/3. That's a fraction less than 1, so this has to be a decay. Part C here, our a this time is 4, our b is 0.25. 0.25 is really 1/4, which would make this a decay. That's a fraction less than 1. And the last one, part D, our a is bigger than 1, which is okay. And our fraction here is 1.75. So that's 1 3/4. That's a fraction, but it's bigger than 1. So that's greater than 1. So that's not a decay. That will make this one a growth because this number is bigger than 1. Anything bigger than 1 automatically makes it a growth. Okay, so those are pretty simple little examples, growth or decay. All right, so now we can determine what they are, what they look like. Let's take a look at how we graph these. Okay, so first graph we have here, this is a number bigger than 1, so it has to be a growth. Okay, so this one's a growth. And all we have here is a simple XY table, and we're always going to use the same numbers. We're going to go 2, 1, 0, negative 1, 2, negative 2. These are the same 5 numbers you're going to use in pretty much all of your graphs if you have to graph these. Okay, so basically these are your X values. We're going to plug these numbers in for our X. So let's do the first one. Our first X is 2. So 2 squared would be 4. So our first Y value is 4. Now we're going to plug in 1. So in for X is 1. 2 to the first is equal to 2. So our next order pair is 2. Okay, let me get rid of this circle. I don't want to make that confusing. All right, our next number is 0 that we're going to plug in. So let's plug in 0. 2 to the 0 power. Anything raised to 0 is always equal to 1. So at 0, y is 1. Negative 1 now, negative 1. So 2 to the negative first. Okay, hopefully you learned this in Algebra 2a. I'm assuming you did. Anytime you have negative exponents, you drop that to the bottom of a fraction and you make it positive. So 1 over 2 to the first power is equal to 1 over 2 to the first is 2. So 1/2. And then lastly, let's do negative 2. So 2 to the negative 2. Let's drop that to the bottom, turn it into a positive. So 1 over 2 squared is equal to 1/4. So our last number in our chart is negative 2, 1/4. Okay. Now what we basically do here is we start plotting these points. Our first order pair is 2, 4. So that's 2 to the right and 4 up. So there's 2, 4. Our next order pair is 1, 2. 1 to the right, 2 up. 0, 1. So that's 0 up and down, left and right, and 1 up. Negative 1, 1/2. So 1 to the left and about a half up. So that's about right there. And then negative 2, 1/4. So 2 to the left and just a little bit up. So there's 1/4. And you can see that this general shape is one of those exponential growth graphs that we saw a little bit earlier. Okay, and there it is. Okay, so it's a very simple thing to do. Make an XY table, 2, 1, 0, negative 1, negative 2. All right, let's look at the exponential decay now. We can tell that it's a decay because the number on the base of the exponent is a fraction less than 1. So we're going to plug in 1/2, and we're going to raise them to all of these x's. So the first number that we're going to plug in is 2. 1/2 raised to the, oops, let me get rid of that. 1/2 raised to the second power. So really this is 1 squared over 2 squared. And you have to square both the numbers. So I said squared and I wrote 4. All right, so 1 squared is 1. 2 squared is 4. So 2, 1/4. Now we're going to do 1/2 to the first. That's a pretty easy one. Anything raised to the first is that anything. So 1/2 to the first would just be 1/2. And we talked about this one, anything raised to 0. So 1/2 raised to 0. Sorry about this, it's kind of hard to write on here. So 1/2 raised to, did the same thing again. 1/2 raised to the 0 power is equal to 1. Anything raised to 0 is always equal to 1. And let's do negative 1. 1/2 raised to negative first power. Okay, this one's a little different. We have to drop this to the bottom of a fraction. And now when you have two fractions and they're divided by each other, you multiply by the reciprocal. So 1 times the reciprocal of the bottom is 2 over 1. So what's 1 times 2? 1 times 2 would just be 2. And last but not least, let's use a little bit of our mental math here. If the power was negative 1 on this one and it was just 2 times 1, if the power is negative 2 now, it's going to be 2 times 2. So this one should be 4. Okay, so let's graph this now. All right, so our first order pair is 2, 1/4. So 2 to the right, 1/4 up. It's real close. 1/2. 1 to the right, half up. 0, 1. 0 up, 0 left and right, 1 up. Negative 1, 2. That's 1 to the left, 2 up. And lastly, negative 2, 4. So that's 2 to the left, 4 up. So from left to right, we now have a decay function. And try to get as close to those dots as possible. And there we have our decay. Okay, so not too hard. We're still using the same numbers: 2, 1, 0, negative 1, negative 2. All right, so those are the math problems. Now we're going to look at some real life situations that come into play. And not everybody's life, but you will see these at some point, whether it's in college or after that in your job. Okay, so our exponential models. This is how you model a real life problem. We have a growth model on the left and a decay model on the right. The only difference is that the growth model has a plus, the decay model has a minus, which should make some sense. Okay. The 1 plus r part is called the growth factor, and the 1 minus r part would be called the decay factor. So hopefully that's some common sense there. So if it asks you what the growth factor is, those are the numbers inside the parentheses, and the decay factor would be the numbers inside the parentheses. Okay, so what are these other letters in the problem mean? We're just going to run through these quick. We'll do an example, and hopefully it'll make some sense. So A, little a, is your original amount. And this will make a lot more sense once you see the examples. Okay, little r is your interest rate, and it must be in decimal form. Okay. And t is time in years. Okay, so it must be in years. All right, so let's just briefly decimal form. So let's say you have 5%. That equals 0.05 as a decimal. If you have 22%, that is equal to 0.22. Okay, so why do we have this 0 here? Anything between 0% and 10% must have a 0.0. Anything bigger than 10%, so 22%, 0.22. Okay, so let's go to our first example. Okay, it looks hard, really not that hard. All right, in the year 2000, the world population was 6.09 billion people. During the next 13 years, the world population increased 1.18% each year. Okay, so that's just giving us some general knowledge about the situation here. Okay, so part A says, write an exponential model giving the population y t years after the year 2000. Okay, and then it wants us to estimate the population for 2005. Okay, so first we need an equation. That's what it's asking us to do. So let's get an equation. So population is y. What is our original? Okay, so remember, it's a1 plus r raised to the t. All right, so let's see what we have here. What is our original amount? Original amount is 6.09. Okay, so y equals 6.09. 1 plus r. What is our percent? This is our interest rate, okay, or our percent increase. All right, so 1.18 would be, it's less than 10%, so it's 0.0118. And I want to go back to this. A lot of times we use interest rate, but this is just whatever your percent is. Okay, so a lot of times it's just a percent, and then in other problems that we'll see later, it's actually called an interest rate. All right, so our interest for this one, our percent increase is need some extra space here, is 0.0118. Make that plus a little nicer. And we want to find X years. So this is here is our model. Okay, our original amount, our percent increase, and here's our time in years. We don't know what that is yet. But what it wants us to do is, for this problem, it wants us to know, well, how much is it in 2005? Well, our original year was 2000. So 2005 would be 5 years later. So if I replace this X with a 5, we should be able to come up with an answer. Okay, so all we're going to do is use our calculator to get this. Okay, so let's see here. I always do order of operations, parentheses first. 1 plus 0.0118. hit enter. Okay, there's the number inside. And now I do exponents next, so I'm going to raise that to 5. And then lastly, do your multiplying. So I'm going to multiply by 6.09. And this should give us the population in 2005. Okay, so in 2005, our population equals, let's go back to the calculator, 6.46. So we're going to round 6.46. 6.46 billion people. Okay, so not too bad. We created an equation, we solved it using our calculator, we got 6.46. All right, so next problem, part B. It says estimate the year that the population of the world will be 7 billion people. So now it wants us to know in what year will there be 7 billion people on the earth. Okay, so we're going to use our calculator again. And the nice thing is we have this table feature on the calculator. So all I've done is I took our original equation, 6.09, 1 plus 0.0118. Instead of, we're not using 5 anymore, we're going back to the original. We're going to do x. So I raise it to the x power. And when I graph that, it doesn't really look like much, but if I hit second graph, it takes us to a table. And you can see here that in the year 2000, we're 6.09 people. The problem we just solved, in 5 years, it was 6.4579, so 6.46 billion. Now, if I keep going down, it wants to know when's it 7 billion. So we're going to stop when we see that these numbers are equal to 7. So 6.6, 6.7, 6.8, 6.9, and we got to 7.01, which is a lot closer to 7 than 6.92. So this x is 12. Okay, so if we started in year 2000 and we're going 12 years, that would be the year 2012. So the year 2012, the Earth will have 7 billion people, and that's what it did. Pretty close to 7 billion. Okay. And last but not least, we have one more formula that we need to talk about. This is called the compound interest formula. So if you have a bank account, this is the formula that they use to give you your interest. Okay, it's a nice big formula, lots of different letters. So let's just see here. The A means, A is the amount of money, amount you have. Okay, P, capital P, is your principal or original investment. Little r is what we talked about, interest rate, and that must be in decimal. N, little n, is number of times compounded, and we'll talk about that when we get to the example. And T, again, is time in years. Okay, so use this sheet as your jumping board for the final example of the section. Okay, so it says you deposit $9,000 into an account that pays 1.46% interest. Find the balance of the account after 3 years when the interest compounds quarterly. Okay, so we're going to use all this information in here to plug in to use the equation. Okay, so A, amount we have. P is our principal, the original amount. So our original amount is 9,000. Parentheses, 1 plus our interest rate. The R is our interest rate. So 1.46, that's less than 10, so 0.0146. 0.0146. N is how many times you're compounding. It's telling us that it compounds quarterly. Quarterly means 1/4, 2/4, 3/4, 4/4. So quarterly would be 4. There's 4 quarters in a basketball game. And then up at the top, N and T, these two N's are the same. So the N down at the bottom is the same as the N up here. And then how many years are we looking for? It says it wants 3 years. Okay, so our T is 3. Once again, all we do is, this is a calculator problem. We have our whole equation. We're going to solve it on the calculator. I'm going to do my parentheses first. So I'm going to do the division first. 0.0146 divided by 4. I'm now going to add that to the 1 inside the parentheses. I'm doing the parentheses first. Okay, so we get 1.00365. Now I'm going to raise it to the exponent, which is 4 times 3. So I'm going to raise that to 4 times 3, which is 12. I'm going to enter again. So all of this on the right, this right here, is equal to 1.0446 and so on. And then the last step would be to multiply it by the 9,000, and that will give us our final money we'll have after 3 years. So times 9,000, and that should give us an answer. So we have 9.9402. So 9402. And how much change do we have? 0.21. No rounding necessary. So 0.21. And this is money. It's a bank account, so we're going to talk about that. So we have $9,402.21 if our bank account gives us 1.46% interest after 3 years. And that's assuming you're not putting any more money in there. You're just leaving the 9,000. Okay, so that brings us to the end of the first section of Chapter 6. We'll see you again tomorrow. We'll work more on these problems. Thanks for watching.